A big strategy that's used in limits goes back to a concept you learned in grade 11. Do you remember having to rationalize a denominator? Now, what does it mean when you had to rationalize a denominator in grade 11? You probably had something like this, 1 over root 3. And you were taught this is not the simplest form. The simplest form, you would have to multiply the top and bottom by root 3 to get rid of the square root on the bottom, to end up with root 3 over 3. And for a student in grade 11, and even today for a student in grade 12, you might ask, why is this more simple than what we started with? 1 over root 3 over 3 seem about equally complicated. If you wanted to know what that was as a decimal, you could type both of them into your calculator and get an answer right away. Now, historically, we have to go back. We're learning calculus, so some of this history goes back hundreds of years before there were calculators. Before there were calculators, the mathematics involved in doing 1 divided by root 3 by hand took a lot longer than having to do the square root of 3 divided by 3 by hand. This was maybe 5 days faster. I don't know. This would take 12 days to do the calculation, and this one would only take 7 days. No, it's not that bad. But you can imagine before calculators how some of these things could be very tedious. And so it happened in mathematics that having a rational denominator made your mental math calculations, or pencil and paper calculations, that much faster. So you rationalize the denominator that way in grade 11. You also rationalize the denominator with binomials in grade 11. And this is the one that we're going to come up with more often because it's related to the concept of a difference of squares. Difference of squares, we factored them yesterday. But with square roots, if you multiply by, and the fancy math word for the same binomial with a different sign in the middle, it's called the conjugate. If I would multiply this by 2 minus root 3 and 2 minus root 3, on the bottom, I'm multiplying a difference of squares, because I have the same thing with a different sign in the middle. And if you drew all the arrows, or as I said yesterday using the English acronym, if you foiled, you don't like that at all, eh? Well, then I'm going to use it a little bit more than I would normally. No, just kidding. If you multiplied it out, well, your 2 times 2, that will be 4. The 2 times the minus root 3 and the 2 times the positive root 3, they'll always cancel out. And then your last square roots, root 3 times root 3 is root 9, which is just 3. And your denominator, all the square roots go away. Because when you multiply by the conjugate, you always get something squared minus something squared. And if either or both of those were square roots, boom, they're going to go away. Works out perfectly every single time. Now, in limits, we are not just rationalizing denominators. Sometimes it's going to be helpful to do the same strategy and rationalize our numerator. And we're going to, right now, we're just developing strategy techniques that when we get into our actual limit questions, we'll have the tools able to solve them. So what's the, what's going to happen in limits is you're going to have to sort of develop a strategy for yourself to say, when should I rationalize? When should I multiply by the conjugate? Well, it's going to often happen when you have a square root. So here, I have the square root of x plus 3 minus 2 on the bottom. The conjugate of this would be the square root of x plus 3 plus 2. And if I multiply the bottom of the fraction by that, I multiply the top of the fraction by that. This is a very interesting advanced strategy, because if you would tell someone back in grade 9, they're like, what are some of the advanced things you do? You're in calculus. One of them is multiplying by 1. And they're like, ooh, that sounds very advanced. And when you get to university, some of the proofs you'll have to do in university calculus, another important strategy that comes up is adding 0. Multiplying by 1 and adding 0 seem like two completely different, like useless things. You've used the adding 0 strategy before. You probably don't remember it. Do you remember completing the square, where you had to add a number and subtract a number? You were basically adding 0. But it's a major strategy that comes up over and over again. So here, we've multiplied by 1. Okay? The top becomes just 2 times square root of x plus 3 plus 2. The bottom, when I multiply this out, it's a difference of squares. So the first two will get multiplied together. They will become just x plus 3. The outside and the inside, when they multiply, you can see they cancel out nicely, so we don't even bother writing them. And then the last ones, minus 2 times the plus 2, is minus 4. Now, when I simplify this, plus 3 minus 4 will leave me with x minus 1. On the top, if you distributed that 2, perfectly fine. Okay? But we're going to find that often we need things factored to simplify them. So we'll often leave things in a factored form in the end. So it would be fine if you had it like this, or if you distributed that 2, that would be fine as well. The reason we leave things as factored as possible is because if something cancels out, it makes our life even easier. All right, I'll get you to try this one. And while you're working on ones where I said you can try it, if you have a question from the one before and I'm walking around, you can ask that. If you're unsure of something, or you want to tell me I made a mistake. All right, a check on this one. So this time, there's a plus sign here, so you'd have to have a minus sign. Multiplying it out. and simplifying. And again, I left it in the factored form here. Now this is the one that is going to be, I'm really typical of what a limit looks like, okay? So we're learning it right now as rationalizing the numerator. What we're going to get to in a little bit is asking this question: what is the limit as x gets close to 16 of the square root of x minus 4 over x minus 16? And we have a problem, because if you think about putting in 16, you'd divide by 0. Does that make sense? And if you put in 16 in the top in the numerator, you also get 0. And the last time I checked, 0 divided by 0 is something quite complicated in mathematics, right? This would be really easy if I changed this question to say, what's the limit as x gets close to 4? You could plug 4 in and find out exactly what number it's going to be. And if it's going to be, like if I plug in 4, I get negative 2 over negative 12, which is 1/6. If I plug in 4 and I get 1/6, that means when I get close to 4, chances are I'm going to be getting close to 1/6. And that's what a limit is saying. As you get close to 16, what does this equal? Because when you're at 16, it's impossible. Okay? Now, so this is off to the side of our head of what we're wondering about. We don't know what the answer to that is. And we're going to see how rationalizing, in this case the numerator, will help us solve this. So I see a square root of x minus 4. I'm going to multiply by the square root of x plus 4 and the square root of x plus 4. In my numerator, because it's a difference of squares, I'll multiply it out. The first one's root x times root x. That'll just become x. Notice when you have the outside and the inside multiplied, they would all cancel out. And then you'd have minus 4 times a plus 4, which would give me minus 16. And on the bottom, I'm not going to multiply this out, and you'll see why that's a good strategy in a second. So on the bottom, I left it factored. And after I simplified the top, what do I notice? I notice that these factors are identical. So I can cancel those out to simplify, and I'm left with just 1 over the square root of x plus 4. So that means that this expression is equal to this expression. And our question that we had here on the right before, the limit as x gets close to 16, this is the same as asking, well, what's the limit as x gets close to 16 in this? And here, you could plug in 16. When x is 16, the bottom is going to be 4 plus 4, 8, 1/8. And we can say, well, if at 16 it's equal to 1/8, then as it gets close to 16, it should get close to 1/8. Now, technically, at 16, this one's impossible, because it's a non-permissible value. We can't plug in 16 because we're not allowed to divide by 0. And this is what limits is really looking at. What are impossible values? And at those impossible values, as we get close to them, where would we expect to be? All right, there's a couple more for you to try rationalizing the numerator, right? And what does this course do? It really pushes your algebra, because this one's got a fraction in it and a square root. So I'm going to give you some time to try B and C. I'll put up the answers in a bit. Feel free to ask if you're on the right track. Okay, so the first one that we're working on right here, there's your conjugate. And when you multiply that out on the top, you're going to get an x cubed minus 1. Again, notice on the bottom, I didn't FOIL out the bottom or multiply out the bottom because it's already factored. I multiplied out the top because it was a difference of squares. And now, x cubed minus 1 is a difference of cubes. And we just learned yesterday how to factor difference of cubes. Might have to look at your notes. If you factor that difference of cubes and take out the x minus 1, it nicely cancels with the x minus 1 on the bottom, leaving us with a simplified expression. How is this going to be a limit question? Well, if I look at the original one, what's the value of x that's a non-permissible value? 1. If I plug in 1, I'm dividing by 0. So the question will be, since 1 is not allowed, what happens when you get close to 1? And in this situation, when you get close to 1, now that it's simplified, can you see that here in the simplified version, you could plug in a 1. You would get 1 plus 1 plus 1, which is 3, and 1 times 1 plus 1, which is 2, and you'd get 3 over 2. Now, for those of you that have done the grade 12 course, to connect this to grade 12, do you remember when graphing rational functions, if you had a non-permissible value cancel in your numerator and your denominator, when you graphed it, you had a hole in your graph? All of these, what we're really looking at with these limit questions is where's the hole? Where's the hole in the graph? This one would have, so if I went like this, this graph has a hole at 1, 3 halves. How do I know that? Well, the non-permissible value of 1, and at a non-permissible value, your graph will either have an asymptote or a hole. If the non-permissible value cancels out, your graph has a hole. Where do we find the y-coordinate of that hole? After you've canceled it out, you can plug in 1 now. And plugging in 1 now gives me 3 over 2, which tells me that if 1 was possible, the y value would have been 3 over 2. And that's the coordinate of the hole on that graph. Okay? The rest of this graph, okay, the beauty of this is we have no skills from grade 12 pre-calculus to graph that one. Well, we have some skills. But this wasn't one of the graphs that you were able to do from grade 12 pre-calculus. And so another thing that we're going to learn in this calculus course is how to graph things we previously couldn't graph, and how to graph them with more detail, even the ones we previously could graph, how we can graph them even quicker and with more detail. Okay. So we're making connections between things that we've done or are about to do and things that we're doing now. And the more of those connections you can make, the easier it is for you to remember the math and to do the math as we go. All right, one more for you to try. Fractions and square roots and differences of squares. As a first step, did you have the right conjugate? Or did you simplify it? So we have more than one option in this question. Those are your two options. How many people did option 1 on the right? Okay. Oh, that's option 2. Oh, man, that gets confused. All right, the green option we'll call option 1 because you guys read left to right. So in option 1, I made a single fraction in my numerator first by getting a common denominator, right? Would you agree that I can multiply this one by root x over root x? And then that would get a common denominator. I could put that up there. And if I wanted to simplify that further, how do you do a fraction divided by a fraction? Flip it and multiply. That would look like this. I still have a 1 minus root x in my numerator, which I could now rationalize. Did anybody try method 2 and make a conjugate of the whole thing? Okay, not wrong. If I did that, my next step would look like this. I'd have an x minus 1, 1 over root x plus 1 on the bottom. And on the top, when I multiply those together, I will get 1 over x minus 1. And a very, very important skill that you started back in grade 8 when you started fractions is you have to simplify, adding and subtracting, multiplying, dividing fractions. Whether you started with the green side or you started with the blue side, in the end, you need your answer to be a single fraction. Right now, I have fractions inside of fractions. Can you see that? Here, I've got a single fraction, but I still haven't rationalized my numerator. So I'll solve both of them so we can see both. Or from this point, if you're working on the blue side or you're working on the green side, you want to get your answer to be a single fraction in the end, as factored as possible. And if you're trying, I guess, as a challenge, if this was graphed, it would have a hole. Can you tell me where that hole would be? So you still have to rationalize that top one. Rationalize the numerator. So we'll look at our answer from the green side, and then we'll finish up the blue side after. So from the green side, if now I could rationalize the numerator by multiplying by a 1 plus root x. Okay. The top is a difference of squares, so it becomes 1 minus x. And the bottom, notice again, I didn't multiply anything out because it was already factored. Now, when simplifying, you can simplify if two factors are identical. And the challenge I said is, this graph has a hole in it. Where's the hole? But none of these factors are identical at this moment. We've got some that look very close. Do you see you have a 1 minus x and you have an x minus 1? Those are very close, but they're not identical. So we can't cancel out a factor unless it's identical, and we can make those identical by factoring out a negative 1. I'll do an interim step. Here we go. Let's see if I can do this easy. Come on, screen. fancy. I'll just add some space. And an interim step in here before this. Why is that purple there? Perfect. An interim step is I could factor a -1 out of the top. And do you see that that would make this x minus 1? And then they would cancel out. Does that make sense? So whenever you have a factor that's almost identical, like one of them is x minus 1 and the other one is 1 minus x, you can always factor a negative out to make them cancel. And because your x minus 1 is the non-permissible value that cancels out, this graph, what was the original equation? 1 over root x minus 1 over x minus 1 has a hole at 1 comma. Because the x minus 1 canceled out, that non-permissible value will result in a hole. And notice now if I plug in 1, you would get 1 over 1 plus 1, negative 1 over 2. That's where your hole is. And we'd be able to say in this equation that the limit as x gets close to 1 will equal -1/2. Okay. Is everybody good for here right now? I'm going to scroll up and finish the blue. Not quite? Yeah, just let me know when you're done. Okay. If I had rationalized the numerator at the beginning like this and ended up with all these fractions over fractions, looking at this on the top, I would multiply this by x over x, and I would get a single fraction on the top. And on the bottom, I still have x minus 1, and here I would multiply this by root x over root x. So technically at this point, because this is over 1, I can imagine I have a single fraction in my numerator and a single fraction in my denominator. And a fraction divided by a fraction is the same as multiplying by the reciprocal. So I would have 1 minus x over x multiplied by, flip this, root x over x minus 1, 1 plus root x. At this point, I could factor the negative out just like before. And have these cancel out. And I get a simplified version on this side as negative root x over x times 1 plus root x. Notice it's slightly different than this one, depending on the method that you take. Those are identical expressions, but they look a little bit different. And again, that's actually one of the reasons I told you, like, in grade 11, you learned how to rationalize the denominator. In grade 12, your teacher might have told you that if you leave a square root in your denominator in grade 12, it's okay. I don't know if that's true or not. You don't remember? Because if you left an answer as 2 over root 3, you didn't lose marks for that in grade 12. If you left an answer as 2 over root 3 in grade 11, you lost marks. In grade 12, they said, we assume you know how to rationalize the denominator, so we're not going to take off marks. But then there becomes a problem in mathematics. What answer do you put in an answer key? Technically, in mathematics, all answers in an answer key should not have square roots on the bottom. So this one would need to be manipulated more to get rid of those square roots. And one of the nice things about the textbook that you have is the textbook follows the rules of what is the simplest form of the answer. So, what I love about the textbook is that when you get an answer, and then you look at the answer in the answer key, it's like a mini proof. Your job is to see if you can manipulate your answer to make it look like the answer in the answer key. So once you've done the question and simplified it, right? Either we did it in the green way and you got this as your final answer, or you did it in the blue way and you got this as your final answer. You would then look at the answer key and it might have a different one. And then you can sort of set it up as a proof where you do the left side and the right side and see if you can manipulate them to make them the same. Question? Yes. So I still have a square root. Good. This answer would be wrong. How would I get rid of that square root on the top here, though? I could rationalize it again by multiplying by the square root of x and the square root of x. And I would get, extend this here. Now I would get negative 1 over x times 1 plus the square root of x times, I would get x on the top. Because root x times root x is x. And then those x's would simplify. And you would get exactly the same as you have on the left-hand side. Yeah, you're right. It did say get rid of the square roots on the top. What I wanted you to see in this question is, depending on which route you take, it could be correct either way. Probably in this one, the green, if we look at the beginning and how it worked out, probably the green was easier because you got rid of fractions and fractions earlier. In the blue method, you had more fractions in more places, maybe made it a little bit more complicated. So at the bottom of your notes now, it says, hey, need some practice, try exercise 1. Since everybody has their textbook here right now, I'll give you some time to work on these. So pull up your exercise book, pages 3 and 4. And again, one of the strategies that you should do when doing homework is not necessarily do all the questions, but find one that you think is a good entry point for you. Maybe you want to do the very first example just to see if you can get it. And if you get it super easy, then skip ahead and see some more. Because there's lots of questions there. It's like, yeah, it's questions 1 to 4, but they all go up to H. You don't want to do 40 questions. Maybe you do. So look for ones that you think might be a challenge and try them. Okay? And when you check your answer and it's right, do not be afraid to like do a little shout out or like a, maybe a little bit of a concealed, you know. I lived with my cousin in university and I was doing calculus in the kitchen and I would be screaming out when I got the answer. Well, not screaming out, but somewhat refrained cheers like that.